first power. This is 1/2 squared. This is 1/2 cubed, right? This is, the next one should be 1/2 to the 4th, right? And so on and so forth. I'm going to keep doing this. Keep an eye on the red number, the one that says 0.875 right now. All right, keep an eye on that number as I add more of these. Yeah, we don't need to see the picture. We can see it right here. So there's another half, half, half. See it filling in? Half, half, half. What's my number? 0.999 something? Keep going. There you go. I have gone out and I have done this 20 times. And my number is 0.9999999 something 0463, right? But I've only done it 20 times. Let's do it 50 times. So I keep going. Eventually I get to what? 0.9999999? Yeah? Okay, but I need some more digits. Let me go 20 digits. Okay, so it's not 0.999 repeating, is it? Not yet. If I keep going though, let's see what happens. You can't see in there, but I always have half of it to fill, don't I? I'm always going to have something left. So what happens if I could keep doing this forever? Like now, let's go 100 times. Look at the decimal. Oh, the computer rounded it. It said, okay, wait a minute, hold on. This is too many nines. Well, fine, I can have the computer go more digits. How about 75 digits? There we go. So as I keep adding, watch what happens. Do you see what's building from the left to the right? Just more nines, right? Just more nines each time. There we go. That's just adding up the first 253 of those things. And look at that. Now, is it truly 0.999 forever right now? I've stopped, right? But it's accurate out to how many decimals? Let me see what I have on this. 75 decimal places. So does it look like this series is converging or diverging to you? Diverge? As we add more and more of these together, what does it look like it's getting closer and closer to? 1, right? 1. If I went out the first 1,000 digits, right, it would be 0.999. At some point, I would have other numbers. And as I do more and more of these, it would start filling in with more nines. You see? So this is our first example of a series that it actually converges, right? Converges, it looks like, to 1. Now, this is the actual series we just did. I have it right there, up there on the board, but also right here in front of you. That's what we did, right? It was a half plus a fourth plus an eighth plus a 16th plus a 32nd, and we did that forever and ever and ever. We can see geometrically from the picture, it looks like this converges to 1, right? It looks like it does. But how do we actually show that, right? How do we actually show that that converges to 1? So before I do it, I'm going to give you the formula for what a geometric series is. So this is a geometric series right here. It's any series that looks like that. I'm going to write it on the board. All geometric series look like this. Sum n equals 1 to infinity, a times r raised to the n minus 1. Know it. All right? Know it. It's on your sheets, but okay, this is, let's start plugging in values for n. If n is 1, what do we get here? 0. What's r to the 0? 1. So we get just a. Plus, now let n be 2. So if I put a 2 here, 2 minus 1 is 1, we get r to the first power, a times r. And the next one, a times r squared, a times r cubed. And that goes forever. That's what a geometric series is. Now, I'm claiming that the problem I just gave you with the shading of the rectangle, or sorry, the shading of the square, I'm claiming that that's a geometric series. Notice that all of these terms, they all have some base raised to a power and then some constant out front. Let's go back to the problem we just did. It was 1/2 plus a 4th plus an 1/8 plus a 16th plus a 32nd plus, right? That was it? Can you see that as this? So what does it appear the A would have to be for us for this to work? 1/2? So if we look at that as 1/2, this would be 1/2, and then plus this would be 1/2 times what? 1/2 to the first power, right? Isn't that 1/4, 1/2 times a half? And then this one would be, I'm trying to get the A's in every one of these, 1/2 out front. And then the next piece would have to be what? 1/2 squared. Do you all see that 1/2 squared is 1/4? 1/4 times a half is an 1/8. Yeah? And I could keep doing this, right? 1/2 and then 1/2 to the third plus 1/2 and then 1/2 to the fourth plus dot, dot, dot. Yeah? So it matches this formula, doesn't it? Matches this formula. So for us, for this particular problem, what would A be and what would R be? A is a half, and it just turns out that in this particular problem, R is also a half, right? So that is an example of a geometric series. This is just to show you that what we were just doing is a geometric series. The big question is whether or not this converges or diverges, right? Does a geometric series converge or diverge? Right? So I'm going to quickly debate in my mind whether or not I want to prove this to you. I'm going to prove it. It's just, we can't not do it. We have to. All right, so the question is, does this converge or diverge, right? Does it converge or diverge? Well, let's try the nth term test first. Okay, let's try the nth term test. I want you all to look at this right here. If I do the nth term, test, I take the limit as n goes to infinity of a times r to the n minus 1. What happens as n goes to infinity? This becomes something like a times r to the infinity, something like that. And this power is only acting on the r, right? So the question is really, what's r to the infinity? Leslie? Well, it depends on r, doesn't it, a little bit? Doesn't it depend on r? Like, if I tell you right now that the absolute value of r is bigger than 1, then what would that go to? Like if I tell you that that number in here, when you take its absolute value, it's larger than 1, what happens if you take a number bigger than 1 and raise it to bigger powers? It gets bigger, right? So if this absolute value of r is bigger than 1, that thing would go to infinity, wouldn't it? Okay? And then what if I tell you that the absolute value of r is less than 1? So what if I tell you that number in there is like 1/2 or 1/3? What happens if you take that and raise it to a bigger power? It heads to 0, doesn't it? It goes to 0. You understand? There's two different scenarios here. If this r is bigger than 1, absolute value, then this thing is going to blow up and diverge. And what can you tell me about infinity? I'm doing the nth term test. What can you tell me about if this thing goes to infinity, what can you tell me? That is not 0, which means we'd have divergence, right? And what if the absolute value of r is less than 1? Then this thing goes to 0, which means what? The test fails. The test would fail. So what I'm getting at is right now, with the geometric series, here's what I can tell you. If the absolute value of r is greater than 1, we've got divergence. Yes? If the absolute value of r is less than 1, I don't know anything. right? And what do we have in this scenario? The absolute value of r is less than 1, which means I don't know anything. You see that? You all following me? So for a geometric series, I tried the n-term test, and all I can conclude from it is that if the absolute value of r is bigger than 1, I've got divergence. I still don't know what happens if it's, well, you know what, we can change this also. Greater than 1 as well, because if it's greater than, what if it is 1? What if r is 1? What is this? A plus, A plus, A plus A plus A plus A forever? And that should just get big, right? All right, so we don't know what happens when the absolute value of r is less than 1. So what mathematicians did is they struggled with this for a while, okay, this very famous series. They struggled with it for a while, and they said, you know what? Remember, there's a way to figure out what happens, right? There's a way to figure it out. But the way to figure it out means I have to come up with that sequence, right? The n partial sum. I have to come up with that formula for that new sequence and then take its limit. Take its limit. Not the limit of the original sequence, not this, but that sequence formula of the n partial sums, and somehow find out what that does as n goes to infinity. So what happened was mathematicians tried to see if they could come up with a formula for this, the S sub n, right? So let's first write down, let's write down what we're trying to find here, okay? Let's write down what is S sub n. Well, that's just adding up how many of these? The first n of them, right? So S sub n is a plus ar plus ar squared plus ar cubed plus dot, dot, dot. Be careful here. What would your last one be? What would your very last one? I'm going to leave a space in front of it on purpose. A r to the, what are we plugging in? N, right? The nth one is what we get when we plug n into this. What happens when we plug n into that? We get ar to the n minus 1. It's just, it's not n up here. It's n minus 1. What I'm asking you to do is basically do this. Replace this with k, k, and n. So first you plug in 1, then you plug in 2, then 3, and then what happens when you plug n into this formula? You get that, all right? So do you all agree that this is a formula for S sub n? Yes? All I would have to do now is take the limit as n goes to infinity of this. But there's a problem. If I let n go to infinity, what happens here is that this sum gets bigger, doesn't it? Like as n goes to infinity, we get more terms, don't we? It's not like this right here. When I'm letting n go to infinity here, I'm just figuring out what happens to that, right? It's not like I add more things to add up here with this. As n gets bigger, this thing starts to go this way. And so we get more plus, plus, plus in here. So I don't know what this is. I have no idea. Any questions on what I've done? So this is what mathematicians were looking at, and they're like, shit, I don't know. What is that? We don't know. We have no idea, right? This formula sucks because it has all these dot, dot, dots in here. So someone figured this out, and it's just clever. Just watch. What I'm going to do is I'm going to take this same equation, and I'm just going to multiply both sides of the equation by r. Okay? Multiply by r. Okay, what happens if you multiply that by r? You get a times r. Now, intentionally, I'm just going to offset it and put it right here, ar. What happens when you, that's what you get when you multiply that by r, you get this. What happens when we multiply that by r? Ar squared. Then the next one, ar cubed, plus dot, 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 dot. What would the very last one be? So aren't we just adding 1 to each of these exponents? Right? If you multiply by r, we added an r here, we added an r here, we added an r here. So it just went up by 1 on each one of those, right? So this last one, instead of it being n minus 1, it would just be what? N. Do you all buy that? Take this equation, which you all said you understood, multiply both sides by r. I want to ask you right now, what is the term right in front of this one? Right in front of it, what is it? A r to the what? What's the power? N minus 1. It's 1 less than that power, right? Like if this was 10, that would be 9. If this was a million, that would be 999,999, right? So this is always just 1 less. You'll see why I wanted that in a second. All right, so we start with this original series. We came up with the nth partial sum. We said, shit, we can't take the limit of that and let n go to infinity because that thing will grow. So instead, we're going to do this weird step of multiplying both sides by r. Right? Now for the really cool step, let's write down what is s sub n minus r times s sub n. In other words, what happens if you take this row and subtract this row? Let's see what happens. Take everything here and subtract all of these. What goes away? ARs go away, right? AR squareds go away. AR cubed goes away. Blah, blah goes away. Blah, blah goes away. Blah, blah. All this stuff in here. And then at the very end, won't this one go away with this one? Right? So what are you left with? A, right? Minus AR to the n. Isn't that what you're left with? And now I'm going to do something really awesome. I'm going to factor an s sub n out of both of these, which leaves me with what in parentheses here if I pull s sub n out of both of those? 1 minus r, right, equals a minus AR to the n. And one more step. I'm going to divide both sides by 1 minus r. S sub n equals a minus AR to the n over 1 minus r. Do y'all follow that algebra? What have I done? I've done something pretty remarkable here. Well, it's not me, someone else did it, but I'm showing it to you. It's pretty remarkable though. What have I done? I've created a formula for S sub n, right? That's a formula for S sub n, but what does it not have in it that this one did have in it? Plus dot, 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 right? So when I let n go to infinity here, this just got bigger, right? Here, there's just an expression. Can you let n go to infinity here? Absolutely. It's not going to make things like, you don't see any dot dots in here anymore, do you? So if I can figure out what happens when n goes to infinity here, I'm done. I will have the actual sum of this series. It will be the sum. So I've got to erase this. So now what I've got to do is to figure out, if I'm trying to figure out what this is, sum n equals 1 to infinity of AR to the n minus 1, that sum I'm going to call S, all right? That's the original geometric series. That S is just the limit as n goes to infinity of S sub n. That was a formula I put up there earlier. It was in bold. I said this is how we define the sum of an infinite series. It's the limit of the nth partial sums. But we have a formula for that now. And that formula is limit, see n goes to infinity, it is a minus AR to the n over 1 minus r. And do you see that the n is only on that r? Right? The n is only on the r right here. That's the only thing impacted by n. And so we're back to the same exact argument we were at before. What if the absolute value of r, well, we were only concerned with one thing. What happens when it's less than 1, right? Because we already know what happens when the absolute value of r is greater than or equal to 1. The series diverged by the nth term test. But we want to know what happens if that's less than 1. Tell me what happens if the absolute value of r is less than 1. What does this go to? 0. It goes to 0. As long as, if this is true, then this goes to 0, which kills this off, which leaves me with what as an answer? A over 1 minus r. Bam, there it is. There's the formula.
So where did the 1 minus r come from to begin with?
Well, the 1 minus r came from factoring out. You're okay with that, right?
Oh, okay.
Right?
No.
Okay, factor out from both of these. Just pull it out. Okay. So check this out. What this is saying is that when you have a geometric series, the r is what dictates what happens. All right? And I have this written in. It's also in your formula sheets right here. There it is. This is big. This is big right here. If you're given a geometric series, then you have one of two things that happen. If this r, whatever that number is, if the absolute value of it is greater than or equal to 1, then this series diverges. Done. But if the absolute value of r is less than 1, then that's what it adds up to be. That's the actual sum of the series. That's the actual sum. Now, in this class, we're going to look at a lot of series in Chapter 8. There are only 2 series we're going to actually be able to find the sum of. Only 2. Geometric is one of them. The other is called harmonic. And that's it. All the other series we study, we will not be able to actually find out what they add up to be. All right? So this is actually a big deal. So what I'd like to do, all you have to know, I wanted to derive this for you because I wanted you to see where the formula comes from. But all you have to know is that on a test. So I want to go back to this problem we just did with the areas, right, of those squares. We had said it was 1/2 plus a 4th plus an 1/8, right, plus a 16th plus ... But then we had said that's 1/2 plus 1/2 times 1/2 to the 1 plus 1/2 times 1/2 to the 2 plus 1/2 times 1/2 to the 3 plus, and y'all were all okay with that idea? And then from that we concluded that that's a geometric series, right? This is geometric. And we said that the A was 1/2, and we said that the R was 1/2 as well, right? That's where we were. But now we can draw a conclusion. Because when we look at our R, what's the absolute value of R? Well, that's the absolute value of 1/2. And what's that? Bigger than or less than 1? Less than 1. Therefore, this series, right? This series right here, I don't want to write it down again. I will. 1/2 plus 1/2 to the 1, and 1/2 to the 1, plus 1/2 times 1/2 squared, plus ... That adds up to be what?
0.
No? A over 1 minus r, right? A over 1 minus r. So what's A? 1/2 over 1 minus 1/2. And that's just 1/2 over 1/2, isn't it? Which is 1, which is what we were seeing, 0.99999, right? That confirms it. That confirms that when you take 1/2 plus a 4th plus an 8th plus a 16th, and you keep doing that forever, that adds up to 1. Converges to 1. The further you go, the closer it gets to 1. Do y'all get it or no? Yes? All right, I have some more examples. I have 9 minutes. I can do one. Let's do D, because I think that's going to seem the most natural to you right now. I'm going to say this several times to you. All right. The instructions here, D, I say, does this geometric series converge? If so, find its sum, right? All right, I'm telling you it's a geometric series by saying that, aren't I? The way I wrote that? Okay. I don't think I need another one, but I will. Actually, the next one would have been a minus. All right. So I'm telling you that's a geometric series, and what I want to know is whether or not it converges or not. If it converges, I actually want to know what it adds up to be. So the first thing you have to do is make this look like a geometric series. You have to figure out what's A, what's R, right? What's A, what's R. So what I would do is see if you can actually find the sequence that creates this. The sequence that creates it. Because we're trying to do something like this. Sum n equals 1 to infinity. And we're trying to get some a sub n here. We're trying to figure out what the formula is that creates that. So let's figure out what that formula is that creates the sequence. This goes back to last class. Look at those numbers. Positive, negative, positive, negative, positive, negative. How do you do that? Negative 1 to the n plus 1, or you could use n plus 3, or you could use n minus 1. Hey, why don't we use n minus 1? Why? Because an original geometric series has an n minus 1 in it, doesn't it? So let's try and use n minus 1 if we can. Negative 1 to the n minus 1. So do y'all understand now I don't have to worry about the signs anymore? Right? I don't have to worry about the signs. Okay, let's look at the top, the numerators. 1, 3, 9, 27, 81. Recognize those? Those are all powers of 3, right? This is 3 to the first, 3 squared, 3 cubed, 3 to the fourth. This is 3 to the 0, right? 3 to the 0. How could I create that? So I'm going to say next to this, I have a fraction. The top is 3 to the what? You got to start at 0, right? That's correct. And minus 1, right? You're looking at the fact that this is really 3 to the 0. This is 3 to the 1. This is 3 squared. This is 3 cubed. This is 3 to the fourth. So you need to do powers of 3 starting at 0, so we're going to use n minus 1 there. Right? That way when I plug in 1, I get 0 up there. What do you recognize about the denominators? They're all powers of 4, starting with 4 to the first, right? 4 to the first, 4 squared, 4 cubed. So I would put down here 4 to the what? N. Right, so that, what I just did, is something that you have to do on Wednesday. I give you a list of numbers, and you should be able to come up with a formula for it. But now we got to go further. We've got to somehow make that look like, we've got to make it look like this. Okay, my goal is to see if I can make that ugly thing look like that. All right? So here's what I'm going to notice first. This negative 1 to the n minus 1 is really up top, isn't it? Like on top, there's a fraction there. I can put those together. Can I put them together into 1 with the same power? They have the same power, don't they? So I can put them together. So this is the same as negative 3 to the n minus 1 over 4 to the n. Do y'all buy that? Put that together with this, put the negative 1 times the 3, I get negative 3, and they're both to the same power. Damn, I really want that. I wish that 4 was to the n minus 1, right? Wouldn't that be awesome? Because then you could put them together, couldn't you? What have we done in the past when we really wanted something to be something? We made it happen, right? So what do I want it to be? N minus 1 is what I want it to be. So what I'm going to do is I'm going to do a minus 1 plus 1. So I'm about to change this to become negative 3 to the n minus 1 over 4 to the n, and then I really want it to be minus 1 plus 1, right? There's my hidden 0 there. And then that becomes negative 3 to the n minus 1 over, now this is just properties of exponents, tell me if you agree or not, 4 to the n minus 1 times 4 to the 1. Isn't that me pulling those apart? Like if I asked you to put these together, right, what would you do? Add the exponents, right? And you do n minus 1 plus 1. That's that, n minus 1 plus 1. So all I did was just separated them. Yeah? Now, all of these, all of those are to the n minus 1 now, right? So I can rewrite that as negative 3/4 to the n minus 1. But what do I still have here? A 4, right, on the bottom? So I'm going to write 1/4 out here. Do you all buy that? And now if I just flip the order of this, I've got 1/4, negative 3/4 to the n minus 1. And do you all see the a and the r now? I was trying to get it to this. I was trying to get a, r, right, to the n minus 1. So for this geometric series right here, what's a? 1/4. What's r? Negative 3/4. What's the absolute value of r? Absolute value of negative 3/4 is 3/4, and that is bigger or less than 1? It's less than 1, and because it's less than 1, we have convergence, because the geometric series says if the absolute value of r is less than 1, we have convergence. What does it converge to? A over 1 minus r. So this right here is going to equal, this sum is going to equal, I'll write it so we have it, a over 1 minus r, because this means we have convergence. And a for us was 1/4 over 1 minus 3/4. Is this 1 again? Yeah. Oh, wait, hold on. No, I almost screwed it up. Because what's r? Negative 3/4. That should be a 1 minus what? Negative 3/4. I remember last semester's test, so many students missed that. Okay, you see? Minus a minus, so it's plus. So this is going to be 1/4 over 1 plus 3/4. What's 1 plus 3/4? 7/4. So 1/4 over 7/4. And then you can flip or whatever. 1/4 times 4 over 7 is what? 1/7. It adds up to be 1/7.
So for this, we would have to write down the test for this one as well, or would it just be?
No, okay, good. You could say this is, on there, I don't think they call it the test. They just say geometric series, right? Yeah, you could say geometric series test if you wanted to. Okay, we are out of time. It's 10:40. So please make sure you go back after the exam on Wednesday. Make sure you go back, review this video if need be. We're going to come in and we're going to go right into, we're going to do some more examples of geometric series. And then we move on to, we're still going to be in this section.